The composition of dry air is relatively consistent, with nitrogen being number 1, oxygen number 2, and surprisingly argon number 3. Carbon dioxide a rather distant number 4. Argon's a surprise at number 3 because no one ever talks about it, well, except for me. The reason is argon's a noble gas, colorless, odorless, chemically inert, it's just there, whereas the nitrogen, oxygen, carbon dioxide, of course, cycle. We can divide the atmosphere up into 4 layers depending on how the temperature varies with altitude. Everyone knows down here in the troposphere that the higher you go, the colder it gets. Surprisingly enough, when you get in the stratosphere, that trend reverses. Temperature actually increases with altitude. And of course, anytime there is a heating of an object, there has to be an energy source. And in this case, it's the sun. Certain wavelengths, ultraviolet lights being absorbed in the stratosphere and lower mesosphere. When we get in the thermosphere, once again, temperature is increasing with altitude and therefore more radiation is being absorbed from the sun. In this case, X-ray and ultraviolet radiation. The thermosphere is not only warmed by the high energy radiation from the sun, the ultraviolet X-rays and gamma rays, it's also ionized. And those ions can reflect certain radio wavelengths. Fortunately, not all wavelengths. Some wavelengths can punch through. And that's good news because otherwise satellite communication and radio astronomy would be impossible. Unfortunately, the very same wavelengths are sometimes used by both radio communication and radio astronomy. The stratosphere is warmed by absorbing a lot of the remaining ultraviolet light. One of the more important substances in this absorption of ultraviolet light is ozone. Unfortunately, we've discovered recently that refrigerants such as your chlorofluorocarbons, freons for example, break down ozone and appear to be decreasing the concentration of ozone in the stratosphere. In the 80 years since the discovery of the Chapman cycle, we've discovered there's a lot of photochemistry occurring up in the stratosphere, and one of the more important natural chemicals up there is water. Unfortunately, we've upset the balance between creation and destruction with our synthetic chemicals such as our chlorofluorocarbons. Laboratory experiments showing that chlorofluorocarbons could destroy ozone didn't answer the question of whether that destruction was significant up in the stratosphere. It wasn't until 1985 that the first solid piece of evidence showed that the chlorofluorocarbons were having a significant effect on the stratosphere.
Once in the stratosphere, the chlorofluorocarbons will remain there for decades.
The bottom layer of our atmosphere, the troposphere, is where most of our weather occurs. Your fronts, your tornadoes, your hurricanes are all basically tropospheric events.
Water undergoes evaporation and condensation, cycling endlessly.
Our 3 basic clouds are the cirrus, which are your very high altitude wispy clouds made of ice crystals, and the cumulus, which are a little bit lower that tend to have kind of a puffy appearance to them, and then the stratus, which tend to be lower than the cumulus and give you kind of a uniform wall-to-wall cloud cover. Now, of course, there are clouds that are kind of in between. Things like the cirrocumulus, the cirrostratus, and the stratocumulus. Relative humidity is the ratio of the actual amount of water vapor in the air divided by the maximum amount of water vapor in the air you could have at that temperature. Because the maximum amount of water vapor you can have in the air depends on the temperature, your relative humidity could be 20% or 80% depending on the temperature for the same actual amount of water vapor. The energy necessary to convert a liquid at its boiling point temperature into a gas is the latent heat of vaporization. Now, nature is symmetric, so what goes in is what comes out. So if you take water vapor and convert it into water droplets, as in a cloud, this energy is released. And if you have lots of clouds being formed, like with a hurricane, then lots of energy is being released. Remember how relative humidity works. The lower the temperature, the higher the relative humidity. Make a cloud, you need to get to 100% relative humidity, dew point temperature. So you got to lower the temperature of the air down to the dew point temperature. The way you do that is get the air to rise, because when the air rises, it expands. And when it expands, it cools. So anything that'll cause the air to rise, mountains, convection currents, cold and warm fronts, has the potential to generate a cloud. When moving air mass hits a mountain chain, it really doesn't have much of a choice. It's got to go up and over. So if you start with moist air to begin with, and you got a tall enough mountain chain, you're going to have rain on that side of the mountain. Interesting thing happens when the air gets over to the other side of the mountain. The air goes down the mountain. As it goes down, it's compressed, and as it compresses, it heats. And as the temperature goes up, the relative humidity goes down. So you got the potential to have lots of rain on one side of the mountain and very little rain on the other side of the mountain. In fact, this is exactly what we've got in the northwest of the United States. Washington, Oregon coast, you've got prevailing winds coming off the Pacific Ocean, hitting the mountain chain, lots of rain. In fact, it's a temperate rainforest. On the other side of the mountain, we've got very dry conditions. It's an orographic desert. Orographic desert is when you're on the wrong side of the mountain. Convection currents are generated by differences in temperature. If the air is being heated, it'll expand, have lower density, and rise. Now, as it rises, it generates a vacuum behind it, and air rushes in to fill that vacuum. You've got a convection current going. During the day, the land warms up more quickly than the water. The land heats the air rises, you've now got a convection cell going. With all that rise in air, our summer afternoon thunderstorms really shouldn't be a surprise here in Florida. Convection currents depend on temperature differences. Now at night, the land cools more quickly than the water, and the convection cells reverse. Convection currents depend on temperature differences. So if you got the right geography, it's not surprising that you can have seasonal convection currents. Summer, the land is warm, the air rises, you get lots of rain. Winter, the land is cool, the air sinks, you have drought. Because of the spin of the Earth, winds in the northern hemisphere curve to the right, and in the southern hemisphere to the left. Low pressure systems are generated by rising air. As the air moves into the low pressure region, it curves to the right due to the Coriolis effect. This rightward curvature generates a counterclockwise rotation in your low pressure systems. In a high pressure region, you got sinking air, and of course the Coriolis effect causes that air to curve to the right. That gives the high pressure regions their clockwise rotation. As the cold air pushes the warm air out of the way, it also takes some of it and lifts it upward. As the warm air is lifted upward, it expands, and as it expands, it cools, and you got the potential to generate clouds and rain. Warm air being less dense than the cold air, when the warm air pushes the cold air out of the way, it also tends to slide upward. And of course, you've now got the potential for clouds and rain. Climate's long-term average weather conditions. And of course the most important thing in determining your climate is how much sunlight do you get. But there's a number of other factors that can also influence your climate. Things like reflectivity, your albedo, or how much dust there is in the air, concentrations of greenhouse gases, geography, where are the mountains, winds, which way are they blowing, oceans. Remember, the water warms up slower and cools down slower than the land, and of course ocean currents. Which way are they going? Are they bringing warm water or cold water past your doorstep? The 1815 volcanic eruption at Tambora threw enough debris, ash, sulfuric acid droplets high enough into the atmosphere that the following year, 1816, is sometimes referred to as the year without a summer. In the 1980s, this effect of dust high in the atmosphere got people thinking about a secondary effect of nuclear war. They calculated that if you had a large-scale nuclear war, you might throw enough dust high enough up into the atmosphere to where the following year might be cold enough to cause crop failures on a global scale, leading to global famine. Sunlight warms the ground, then the ground glows in the infrared region. The greenhouse gases are good at absorbing infrared radiation. The infrared radiation warms the greenhouse gas. The gas now glows in the infrared region also. This absorption and re-emission of infrared radiation slows the loss of heat, making the Earth warmer than it would be otherwise. The greenhouse effect of carbon dioxide has been known for, about 100 years. The question has always been, is the concentration of carbon dioxide that we humans are generating in the atmosphere significantly high enough to affect the global temperature? In fact, we're still debating that as scientists, and the politicians are still debating what to do about it.
Global production of carbon dioxide has increased from 19,411 million metric tons in 1980 to 35,666 million metric tons in 2016. Atmospheric concentration of carbon dioxide has been increasing every year. In this plot of temperature variations for the last 1,000 years, it can be seen that temperatures naturally oscillate, but that there has been a steep increase lately.
Winds are number one and ocean currents are number two for transporting heat from the tropics to the poles. In the three-cell model, air rises at the equator, giving rise to the doldrums. You'd expect to see rain here, because remember, anytime you got rising air, you got the potential for rain. The air rises and then sinks again at the horse latitudes. And anytime you got sinking air, you'd expect dry weather. Connecting that sinking air at the horse latitudes with the rising air of the doldrums, you got the northeast trade winds. Notice that the winds curve to the right because of the Coriolis effect. Now, if this three-cell model was the total picture, the United States would be one big desert, because the horse latitudes run right about through the middle of the United States. Fortunately for us, it's not the whole story. For one thing, remember, convection cells are generated by differences in temperatures, so you'd expect some seasonal shifts in those boundaries between the zones. Also, remember, land warms up faster and cools down faster than the oceans. So you'd expect some ripples in these lines wherever you've got boundaries between continents and oceans. But the most important factor is the atmosphere is chaotic. Little instabilities lead to big changes, leading to things like fronts. And remember also, we've got our little local weather systems like the sea breezes here in Florida. The dynamic nature of the Earth's atmosphere is illustrated rather nicely with the jet streams. You've all seen on the weather reports plots of the jet streams, and they'll be saying things like, oh, there's this big bend in it that's pulling cold air down towards us. Well, the jet streams mark the boundaries between our global convection cells. So this illustrates nicely that the atmosphere is very dynamic and chaotic. Short-term weather prediction is a matter of looking at the blocks of air move relative to each other. If you got continental polar air moving towards you, well, it's going to be cool but relatively dry. If you got maritime tropical air moving towards you, well, it's going to be warm and rather moist. Long-term weather prediction, you really can't do it because the atmosphere is too chaotic. Water warms up slower and cools down slower than land, so your coastal areas tend to have warmer winters and cooler summers than your continental interiors. Your ocean currents can also transport heat from the tropics and transport cold from the poles as well. The combination of the global prevailing wind systems and the Coriolis effect generates large-scale circular surface currents we call ocean gyres. Each of the great ocean gyres got a variety of names depending on what part of the world it happens to be going by at the moment. For example, the North Pacific gyre, known as the California current, as it sweeps past the west coast of the United States. As it heads towards the equator, becomes logically known as the equatorial current, or more exactly, the North Pacific equatorial current. The North Atlantic gyre, that part of it that sweeps past the United States, known as the Gulf Stream. And the Gulf Stream brings us nice warm water on the east coast, where of course the California current is bringing nice cold water past the west coast. The Gulf Stream of course also dumps a lot of its heat over in the North Atlantic, helping to warm Western Europe. The Labrador is an interesting one. Actually starts out as an eddy from the North Atlantic gyre, loops through the Atlantic, and then brings nice cold water back down by the United States. The Earth's climate is not stable. It looks like over the last few million years that about every 100,000 years we enter into a major ice age. Milankovitch has shown that the gravitational perturbations of the Earth with other planets lead to tiny, regular changes in the amount of sunlight hitting the poles. And furthermore, he says that these tiny changes in the amount of sunlight hitting the poles can lead to the beginnings of an ice age. All you have to do is have a little bit of snow left over from last winter. Each winter, you start off with more snow, you eventually end up with a big glacier, you've got an ice age. There are three major changes that occur on the Earth due to gravitational interactions with the other planets. One is precession of the Earth's spin axis. That is, the North Star is not always going to be the North Star. The Earth's North Pole sweeps through the sky, pointing at different stars over time. 23,000 years, it'll be back to Polaris, our current North Star. Also, the tilt of the Earth's axis changes a bit over time, which means that the Tropic of Cancer, the Tropic of Capricorn, the Arctic and Antarctic Circle are slowly moving all the time. And finally, the shape of the Earth's orbit changes over time, becomes more elliptical, and then becomes more circular, and then more elliptical again.